All right, thank you, Jason, for the wonderful introduction. So yeah, Steve made a great presentation about how to get started with vLLM, how to spin it up, how to insert some tokens, get some tokens out, and now we can dive into what happens behind the scenes. So vLLM has emerged as kind of the de facto open source generative AI inference platform, and it's done that by positioning itself at the center of all the major open source models and all of the AI accelerator hardware providers. And the first goal that vLLM has is to be the fastest and easiest to use open source LLM inference and serving engine. And the second goal it has is to support any model, any optimization, any accelerator, and any cloud. And what this does is it gives users the flexibility to satisfy their needs while getting the best utilization of whatever hardware they have available, right? So you might have hundreds of nodes of latest NVIDIA GPUs, or you might just have kind of like a customer, not customer, but just regular user kind of like desktop GPU. No matter which one you have, like vLLM will try to support all the models and all the optimizations to give you the best performance possible. So what we'll talk about today is, first we'll talk about what problem is vLLM actually solving. Then we'll walk through a few of the core vLLM optimizations. And then finally, we will look at the Torch.compile integration. The reason that that's separate and not under one of the core optimizations is because it kind of exists in its own plane, and it enables like a whole new class of optimizations, as well as adds some other additional benefits and flexibility that we'll dive into later. So the problem that vLLM is solving is production inference serving, right? So here we're talking about batch size much greater than 1. On data center hardware. So we have a lot of users, we have a lot of requests coming in concurrently at the same time, and we have beefy data center hardware to deal with it. Like, how do we do that as efficiently as possible? And this is in contrast to kind of the workload of an on-device inference for a single user. So somebody just interacting with an LLM one-on-one on their laptop. Like, that's kind of the opposite use case. And the big questions that we need to figure out are, how do we efficiently schedule the requests into each forward pass of a model? And how do we manage KV cache context and runtime memory footprint efficiently? So why is this hard, right? Why do we need something like vLLM at all? Why can't we just kind of spin up a model like with a few lines of PyTorch code on our own laptop? So an LLM at its core is a function that predicts the next token given all the previous tokens in a sequence, right? And so to generate a bunch of text, we chain together a couple of forward passes through the model, right? And so a single request will require multiple passes, and it might last for even a few seconds, even though each forward pass is on the scale of milli or even microseconds at this point. So on this diagram, you can see the tokens going kind of left to right, and the forward passes going top to bottom. So first we start with no tokens. We insert the yellow tokens, which are the tokens that the user provides, the prompt, right? And then with each forward pass, we generate a single new blue decode token. And then finally, once we get the red ends token, that means we're done. The request is finished. The LLM says it's done with producing the output, and we can move on. And this is a single request, right? So now the challenge is, how do we do that for multiple concurrent requests at the same time? And so we need to batch, right? So we're all familiar that AI hardware is much better at processing multiple things at the same time rather than one at a time. So we have to somehow batch these requests together. And this has been happening before, but the key difference is that we don't know how long, we need multiple forward passes, and we don't know how long a single request will be. So before, if you needed to classify a bunch of images, you could just batch 1,000 images together, run them all through the model, get 1,000 outputs, and then move on to the next batch of images, which is kind of like a naive batching approach. If we did that for LLMs, we would get what you get in the top, what you see in the top diagram, right? So we batch five requests together, and then we generate tokens. But as the requests finish and others don't, we are suddenly just wasting a bunch of compute because we're not utilizing the request slots well. Because we're kind of, we have to finish running the batch through until all requests finish. So instead, what we can do is this technique called continuous batching. With continuous batching, with every forward pass, we check if any request is finished, and if it has, we can replace it with a new request coming in. And you can tell just by looking at the colors in the diagram and the length of it that this is much more efficient at utilizing the hardware and getting requests finished as soon as possible. And this diagram isn't even showing the full picture because with each forward pass, we can actually change the batch size. So maybe we start with 5 requests, and then as more requests come in, we can actually add even more to utilize the hardware even better. The next challenge that we have to deal with is KV caching. So a key component of transformer models is self-attention, right? In self-attention, we have the query, key, and value tensors, and we have to kind of like attend each of them to each of the previous tokens. So we have these token embeddings for each of the tokens, and we have to compute this kind of cross product. And obviously, once we get to the next token and the next token after that, we are recomputing all the kind of cross products between the previous token that we've already computed. So that's all redundant. And instead of recomputing it, as you can see in the top part of this animation, we can just cache that and only compute values relevant to the new token that's going through. And this way, we don't actually have to remember any of the previous tokens. We just have to cache these K and V values as we do this forward pass through the model. And you can see that on top, the QK tensor is growing kind of quadratically, and on the bottom, it's growing only linearly. So the compute still increases. We're still doing more work with each new forward pass as the sequence grows, but it's not as dramatic as if we were recomputing everything. So this is all great, but it needs a lot of memory, right? So now that we are storing these K and V values, we have to store them on the GPU, and that takes up a lot of memory. It can be megabytes per token. So for long sequences, this can be gigabytes. And so in this diagram below, you can see kind of like an A100 with 40 gigabytes. Let's say we're running a model with roughly 60% of the GPU memory for the model parameters for the weights, and then if the KV cache takes up the other part that's still available, because you still need some space for activations, you need space for CUDA graphs, some other GPU memory like driver memory, etc. You're only left with, if I can read this, I think 12 gigabytes, and that's not a lot. So you want to manage this efficiently, right? Why is managing this efficiently hard? Basically, you need to know how much memory you're going to need ahead of time. And that's pretty much impossible because you don't know how long the request generation will be. So either you allocate less than you need, and you have to keep reallocating and copying, so that's inefficient, or you allocate way more than you need, and you're just wasting a bunch of space, like that space is sitting idle while other requests are starved for memory. So instead, we can take a page out of the Linux kernel book and implement paging, right? So the original innovation that vLLM was started on was PagedAttention, where instead of kind of allocating KV cache as a contiguous block, you implement this kind of layer of in between that's called the block table, where logically, so virtually speaking, you have a contiguous block, but physically, these are kind of blocks that can be allocated anywhere. And as you grow the KV cache, you can just kind of keep adding blocks. And the reason this is important is generally, kernels will take in tensors that are contiguous, so you need special kernel support that can take in this block table and read the memory indirectly from the appropriate block as opposed to from a contiguous block. So now let's try to combine PagedAttention and continuous batching. We have 2 requests here, A and B, A on the left and B on the right. And on the left in request A, We have Alan Turing is a computer scientist and mathematician, and the token that's currently being generated is going to be renowned. And so we can see that request A sees the blocks as just kind of like contiguous logically, but then physically they're scattered all over kind of the KV cache memory. And this block table isn't filled in. I thought this was going to animate, but so you can imagine kind of like the first block being mapped to block number, I think that's 7, and then the second block being mapped to block number 2, and so on. And same for request B, we have this other sentence and these other blocks that are kind of getting filled in, and we allocate a new block for the token renowned because we ran out of space in the previous block, and so on. All right, so the next optimization that I'll talk about is quantization. What is quantization? At its core is just using lower bit precisions for storage and computation, whether that's floating point 8-bit, 8-bit integers, or even 4-bit floating points with the newest NVIDIA hardware. There's kind of like 3 overall strategies for quantization. The first one is just weight quantization. What weight quantization brings us is reduced storage and memory footprint. So a 100 billion parameter model stored at 16-bit precision will take 200 gigabytes, right? But at 8-bit precision, it will only take 100 gigabytes in memory. And with LLMs, weights actually take up way more than activation. So this is really important, right? How expensive storing the weights is. The second benefit here is also loading of the weights. Like as you compute through the model, you have to load the weights from global memory into kind of shared memory or registers, whatever you use to compute with, and that takes up bandwidth. So if your weights are smaller, then you can load them faster. The second is activation quantization. So if you combine weight and activation quantization, you can not only load the weights faster and take up less space, you can also compute faster. Because just like memory bandwidth, compute throughput is also related to kind of the bit size, because the number of bits you can compute with per second is pretty fixed, comes down to physical limitations of hardware. So if you can compute with smaller data types, then you can compute with just much faster. And then finally, KV cache quantization kind of combines both of them as well. Storing a large KV cache, especially for really long sequences, is much easier if you're using a smaller data type. And then KV cache is used in attention computation, which is a large bottleneck. So computing at the lower data type is better as well, and faster. But you also lose some accuracy with some of these quantization techniques. We've actually gotten some really good recoveries where it's barely noticeable, but vLLM is very flexible, and it lets you combine KV cache quantization, activation quantization, weight quantization in pretty much any way you want to get the kind of the accuracy and speed up and memory regime that you want. So all of this is configurable. And so we can see kind of some numbers for the impact of quantization. I think the takeaway is that quantization enables more tokens on the same hardware, right? So if you have some fixed hardware, like now suddenly with quantization you can produce a lot more tokens per second. In this plot you can kind of see there's 2 regimes, right? In the kind of low queries per second, that's on the x-axis, so basically how many requests are hitting the server per second. On the y-axis you have the time it takes per output token. And so obviously the time goes up as there are more requests are hitting the server, right? That makes sense because the GPU is being shared across more requests. But the key takeaway from this plot is that in the low QPS regime, the weight for quantization in yellow and activation 16, so not quantized, is actually better than weight 8, A8. And that's because in low QPS, what matters most is how quickly can you load the weights, right? As we move to kind of like a higher QPS regime, the weight 8, activation 8 becomes better because now it matters like your compute amount. So suddenly it matters how fast you can compute. And with weight for activation 16, you're not actually getting any compute savings. But you can still see it's still better than kind of the 16-bit unquantized performance overall. And this comes again back to like what QPS are you running? If your server is running like really high QPS, then you should definitely do activation quantization. If you're just running like kind of lower QPS and you might be able to get away with like super low weight quantization and no activation quantization at all. And it's not in this plot. We also have this W4A8 support And yeah, there's much more here, but just kind of a brief overview here. All right, next one, automatic prefix caching. So this one's very simple. Very often requests include kind of system prompts, right? So, you know, an LLM service provider will say, okay, before every user prompt, insert this kind of system thing that doesn't change. The LLM is, without prefix caching, always recomputing all that. So instead, this prefix in red, why don't we just like compute it once and just save it? And that's exactly what this is. And we can see that, you know, as the cache hit rate goes up, so as the requests are sharing more and more of their prefixes, the performance improvement is better and better from prefix caching. At 0%, you can tell that there's basically no difference. I think there's a tiny little like overhead from prefix caching, because if it's enabled, you have to kind of check every request to see if the prefix fits. Obviously, like the more requests you have coming in, the smaller this difference is, because it's mostly done on the CPU, but just still something worth saying. Like if you anticipate no prefix sharing, like no need to turn this on. And then I think this is the last one, speculative decoding. Basically, we can accelerate decoding further with speculating the tokens, right? There's a variety of methods, but overall, they all work like this. So we've already talked about how processing multiple elements at a time is better, right? And maybe we can't get far enough with batching. Maybe we want even more parallelism, right? So what we can do is we can kind of like introduce this small model called a draft model. And the small model predicts, just generates the tokens as normal, but because it's much smaller, it does it really fast. And then we use these tokens produced by the small model to just verify with the large one. And verification can happen in parallel, right? Because we already have all the tokens. The reason that generally LLMs have to go one by one is because each token depends on the previous. But here we have some guesses, and we can just use the guesses to generate the next tokens, and then we just verify them. And so in this case, actually, the small model produced all the right tokens, and so we can just kind of move on to the next one. But let's say instead of several famous songs are the large model, which is the answer we finally want, right? We can't just use the small model because it won't be as accurate. It wouldn't be giving us what we want. So let's say the large model produces several famous movies are. So in that case, we would say, so songs and movies don't match. But the large model has already generated movies, so then we can just regenerate R. It's likely it's going to be the same, but we don't know that yet, right? Because the large model ran with songs as the previous token, not movies. So now we need to rerun from there. And so we still computed 3 of the 5 tokens efficiently, right? Instead of kind of, so instead of just 1, and that still can be better. So here are some plots. The same format. So on the x-axis, we have requests per second. On the y-axis, we have latency overall. We can tell that the speculative decoding is much better at lower QPS, and then at higher QPS. I think all of you guys in the room should be able to figure out why it's slower at higher QPS. So I'll give you a second to think about it. You know, the exercise left to the reader, or what's that thing in math textbooks? So just to make sure that nobody gets left behind, basically, like, as we scale up the requests per second to be high, like, batching can already parallelize the requests well enough that the extra kind of parallelisms from spec decoding is no longer beneficial, and then the latency actually gets worse because now we're just running all this extra work from the small model, and also we're failing sometimes to produce the correct tokens, and, you know, rerunning, and we're not getting any benefit from it. So that's why there's kind of a pathological scenario for large QPS. And finally, we get to see all of these optimizations run together in action here, right? So on the left, without optimizations, we can see we kind of go through the whole prompt slowly. On the right, we have prefix caching instantly kind of like go through the system prompt. Then the prefill phase does like the whole prompt at the start. Then with spec decoding, we can get through the stuff faster. With FPA KV cache, we can load the stuff up faster and generate faster. There's also, you know, if there's quantization happening, it's letting us do things faster. So all of these optimizations kind of work together in vLLM. Yeah, so over the last 2 years, vLLM has rapidly gone from just a research project from, like Steve mentioned, Ian's lab at Berkeley, to kind of the open source default. Some stats here. This is the paper that, the kind of front page of the paper that Steven also mentioned. I actually gave a version of this talk in July, and I had to update the number of stars from 50K to 58. So just still growing. And yeah, I think we pride ourselves the most on having just a very vibrant kind of contributor community. So there's over 1,000 people that have contributed to this project, and it's really what makes working in it great. So yeah, I think from kind of the base of just PagedAttention and KV continuous batching, we've built this this system that can handle any kind of model, from state-of-the-art LLMs to multimodal hybrid embedding, encoder, decoder. And it has all these optimizations in them, and then it runs on all these kinds of hardwares. And I think having this kind of vibrant community really comes from like this separation of concerns. Like model writers can just focus on writing models, and then people writing kernels can just focus on writing kernels. Like hardware providers can just focus on like providing like a good performance on their hardware. And a big way that we achieve this is through Torch.compile. So let's get into it. What is Torch.compile? Just really briefly, it's basically just a just-in-time compiler for PyTorch code. So if you have a PyTorch function, it takes two tensors, does some operation on them, returns some product. When you annotate it with Torch.compile, it will trace this function. So it'll use the inputs that you give it, and it'll trace through it, produce an FX graph. Then that graph gets lowered into Triton kernels, or if you have your custom kernels, it'll invoke those. And yeah, it can give you very efficient code for, while still kind of preserving the simplicity of the eager mode PyTorch. And this is kind of a useful flow chart on when to use Torch.compile and when to not. Do you want to spend hours, days, weeks writing fast optimized kernels? If no, use Torch.compile. If yes, and you did, is your kernel actually faster? If no, just use Torch.compile. And then if it was faster, great, perfect. You got a faster kernel. That's great. And the support for custom kernels is still just as good in Torch.compile. Like it doesn't preclude you from using them. And kind of the large goals that we have in our vLLM Torch.compile integration are, one, automatic kernel generation. So what this lets us do is just like very fast iteration, like new models, new features, like new approaches. We get just fast kernels at very little cost. We get automatic fusion across layers, and we get performance portability, right? So with this kind of approach where you can just simply write one kernel and it runs on all kinds of hardware, that's much better than like optimizing a kernel, which you have to do for each hardware platform separately. Some of the operations that use this is rope, RMS norm, CLML quant, like all these kinds of like smaller operations that don't contribute enough to the running time to be worth like really optimizing for months, but at the same time, like, they're still important enough that they need to be fast. Like we can't afford to have them be too slow. And then the second thing is we have some optimizations that we want to kind of apply independently of model definitions. So whether that's just like fusion of things across layers, or piecewise CUDA graphs where we exclude a bunch of operations from CUDA graphs, or maybe even some more complicated like graph level transformations when we overlap, like we restructure the model forward pass and we overlap kind of compute and communication and so on, like nanoflow or double batch overlap, micro batching, whatever you've heard it be called. These are things that are really hard to do in model definitions. Like you basically have to take a model definition and you have to like completely like do surgery on it and change it up. And that's just not scalable, right? For every optimization, like there's X optimizations and Y models. Like we can't be doing like X, Y work for all of these, right? But instead with Torch.compile, we can just kind of do the optimization ones and like apply it to all model definitions. Or not even apply to model definitions, like apply to all models. And then people writing model definitions can continue to write kind of simple expressive code. So currently, the passes that we have are, there's a bunch of quant fusion. So quantization always happens at the start of, like, right before like a scaled matrix multiplication, right? So first we take inputs that are not quantized, we quantize them, which is memory bound because you're just reading, then doing a tiny bit of math and then writing back out. And then you're doing kind of your matrix multiplication, right? So this quantization always, very often follows something else, and it can just be done like on the output of the previous operation. So we have a bunch of these fusions. You can see the performance numbers. These are end-to-end performance numbers, so these are pretty significant. Like 7% end-to-end is pretty good. 11%, that's a little bit of a lie because it also there's this includes the speed up from the FPA KV cache, but it's just kind of how the kernel is structured. Like you can't do just KV cache. You have to do KV cache and quant fusion and so on. These are kind of the custom op fusion that we have. Then we also have a bunch of collective fusions. So as I mentioned, like there's communication overhead, right? So if you're running on multiple GPUs, they have it synchronized like that. You're just using the network. You're not using kind of the compute part of your GPU. So ideally, you want to overlap that with the compute part. So we kind of try to do that by overlapping some of these operations and fusing them into the same kernels. And here's a couple of the passes as well. And I'd be more than happy to talk after this, or if people have questions on the specifics. But I just want to go into the examples. Oh yeah, we also have a couple of utility passes. This is just like, if there's a bug in Torch.compile, or if there's just something we want to do specifically to the graph, we kind of just we can just write a pass and edit the graph however we want and fix an issue or something. These aren't necessarily to improve performance, just to make sure things are running smoothly. So yeah, I just want to run quickly through an example of a fusion pass. So we're going to look at attention and quant FP8 fusion. Basically what we're doing here is we have this OPROJ linear layer that follows attention, right? And so the order of operation is attention, which produces the output O, then quantization of the output O, and then a linear layer which, multiplies, does a matrix multiplication with the quantized output and the quantized weights to produce kind of the final output of like the overall attention structure in, Llama or many other models. So we want to fuse this kind of quantization at the start of this OPROJ linear layer to the attention beforehand. And we do that by using the inductor pattern matcher. So this operates on kind of this FX graph that the Torch.compile produces. And we can just kind of fuse the kernels using the pattern matcher. So the pattern matcher, what that does is it takes a pattern and it takes a replacement. And anytime it sees the pattern in a graph that you give it, it replaces it with the replacement. And but by doing that, we can kind of fuse these two operations without any impact to the model definition or the linear and attention abstractions, right? So in this like top diagram, you can see the linear layer for OPROJ and the attention layer for attention, like they're separate. So we can't just like move things in between them without changing them and doing surgery. But if we do it at this like FX graph layer, then we can do the fusion and get the maximal performance, and not sacrifice kind of our abstractions. So yeah, on the left, I've kind of emphasized some of the tensors in the pattern and then the replacement. So in purple, you can see the output of attention, right? And then it gets passed into the attention function as kind of the output tensor to write into. Then we get it back out, and then we pass it to the quant function as an input, and then we get the output of the quant function in blue, and the scale for the quantization is in yellow, right? In the replacement, you can see there's no more output of attention, right? No more purple, just the output of quant, which attention will write directly out to. In this case, the op for the fused kernel is actually the same as the previous. We just pass the scale to the attention op, and then the attention is like, okay, you passed me a scale, which means I need to quantize my output as I go. And on the right, you can see the kind of the profile for the two forward passes. The top one is without the fusion. The bottom one is with the fusion. And you can see that in the top, we have these three kernels, right? And they're like highlighted. So we have the green and pink, both attention kernels. Not really sure this is on ROCm. I think there's a separate attention kernel. Not 100% sure what this one's doing, but it stays top and bottom, it's the same. And then the green one on the left is kind of the main attention kernel. And then on the right, we have the green on top with the quantization kernel, right? You can see on the bottom, one, the quantization kernel is completely gone, so it's not there at all. And then two, you actually see that the green section, the large one, is actually smaller. And that's because suddenly attention is writing out in quantized outputs, and that saves a lot of memory and bandwidth, which means that it's now faster. So we kind of get the double benefit of like one, eliminating quantization overhead, and then two, even speeding up the attention itself. And yeah, so I think I don't know if you can see the numbers, but I think it goes from like 52 microseconds to like 47. So I think almost 10% improvement on attention. And that kind of leads to the end-to-end 7% that I mentioned earlier. So yeah, what are some future goals for our integration? One is fast startup. So if you watch Steve's demos, you actually know that this is no longer a problem because vLLM starts up in, what, 3 seconds, something like that? No, but jokes aside, we know that this is an issue sometimes because, you know, especially for users trying to just develop or like spin up a quick instance and test things out. Like right now, vLLM takes a while to start up, and for good reason, right? So we take this time to like, you know, record CUDA graphs, like do Torch.compile. Like there's a lot of optimizations that we do to give you the best performance, and the cost of that is sometimes startup time. But we know that this needs to be more flexible, and so we are actually going to introduce these optimization levels that are going to let you trade startup time for performance. So there's going to be O0, which is going to start up as fast as possible and not give you the best performance. And there's going to be O3, which is going to, you know, maybe take a while to load up, but then really give you kind of the best performance possible. And there's going to be 1 and 2 in the middle as well. And then we might even add some word-based ones. Maybe there'll be an O fast that just sometimes trashes accuracy just for no good reason, because, you know, we want to stay consistent with the compiler community and so on. But yeah, so, you know, this is the first focus area. The second focus area is going to be this feature orthogonality. So remember the 4 ANYs that I mentioned, right? Any model, any hardware, any cloud, and any optimization, right? So we want to continue that, and Torch.compile really lets us do this, but we need to just kind of expand this orthogonality to make sure like all kinds of quantization are supported with all kinds of fusion and are supported on all backends and so on. So we still have work to do there. There's currently some work going on where, you know, some piecewise CUDA graph stuff does not interact well with some other passes, so we're addressing that. And then more fusion. So yeah, I think the end goal is to get as much fusion as possible. We know there's still more that is out there, so we need more fused kernels. We need to just like write more passes. And we have some custom ops to unwrap as well, because currently there's some stuff that's hidden from Torch.compile that we want to unhide. And yeah, so if you want to learn more about vLLM and Torch.compile or just vLLM in general, so here's a blog post that we posted somewhere recently. There's a design doc that's a little bit outdated, but is getting updated, so it will be relevant. We did a presentation in office hours that talks more about kind of the baseline stuff with Torch.compile integration. Includes like some of the caching work and so on. And then, yeah, please get involved, join the vLLM Slack. You can browse the issues with Help Wanted if you want to contribute. Like, we love contributions from the community. There will always be somebody to take care of this. You know, review our PRs, get them merged. Like, it's really, like, I think one of the easiest places to get a PR merged in the open source community. And yeah, if you want to specifically, you're interested in Torch.compile, there's the SIG Torch.compile channel on Slack. There's the Torch.compile label on GitHub. If you're interested in startup, whether that's because you want vLLM to start up faster, and just, you know, tell us that, we'd love to hear it. Slack channel and label as well. And then you can connect with me on GitHub. I'm a proud owner of the Pro Expert Prog GitHub handle from when I was 14 years old, and I think now it's too late to change, so I'll keep it around as a bit. And that's it. Thank you so much. Yeah, questions?
So 2 questions. First, curious if you ever try enabling huge pages in the kernel to see if there's a good impact on the latency. Second question, when you were showing the speculative coding with the autoregressive model being a small but much more compute intensive than passing to a dense model, now where we see most of the people more leaning towards a mixture of expert models with the selective activation of the neurons. So we tested vLLM with the MOE as well. It works perfectly. But when we compare, to be precise, say Qwen3 32 billion dense model with vLLM versus the Qwen3 3 billion active per token, obviously the MOE is much faster by means of latency, but the accuracy is lower. We were wondering if there is a reason, or that we can do any vLLM configurations to make the things much better with the mixture of experts.
So you're asking for like a MOE, like higher accuracy?
Correct.
I'm not 100% sure. I would say generally the rule of thumb is just, I guess, go to a larger model if you can with MOE, because I think especially like you said with MOE, like it's sparse, so even a large model actually activates smaller parts of it. So I think you can just go larger, right? Like if you were running like a 30 or 70 billion llama, like you can instead for an MOE run like, I don't know, over 100 billion. But I'm not actually familiar with what the like model sizes are. So I think, yeah, I would just say go larger model. I'm not really 100% sure, or just, you know, ask the labs to give us better models. Like we usually kind of make the models worse, if anything, and faster. We don't necessarily do anything to like make them better. Just try to preserve the accuracy of the original models. And then to answer your original, easier question, huge pages, I assume you mean like increasing the block size in the paging mechanism, right? It's configurable. So I think you need an attention backend that supports it because there's some limitations. I think some backends only support specific block sizes. But if you have support from the attention backend, you should be able to do a larger block size if that fits your needs. Like it's obviously a trade-off between like you know, less fragmentation, but also like using less memory and more waste. But yeah, I haven't myself played around with that.
Huge pages, you gotta enable kernel farm to use the huge pages. I was wondering if vLLM gonna support use of huge pages for bigger page attention cycle.
So this is actually not using like the Linux paging mechanism. Yeah, this is like custom. Like we literally allocate like a huge block of just GPU memory, and then we custom, like it has its own paging mechanism. So I think, sorry, I was just like inferring that you're talking about the equivalent of huge pages. Like no, this doesn't have anything to do apart from like the way it's built with the actual like Linux paging. So you don't need to mess with like huge pages being mobile. You can just specify the block size. Go for it. Yeah.
vLLM in particular, you have to essentially match the full cache in the prefix of the prompt. And is there any ongoing effort at moving towards something closer to like how a drop of quad is able to match like partial hits in the cache? So if you get, for example, have an LLM and you have like, it's like 30 tool calls in the message. What I've seen you do at quad is you can just drop it to like one tool call, hit the cache. Send it tool 3, not 1 and 2, which would break the prefix cache here. I don't know if there's any like ideas or concepts there, especially that I think you probably have to know something about the model.
I think so, and I think you could probably like jam it through, but you would risk just like getting a different outcome. Like we don't really work a lot with like trying to, you know, change what happens. We're just kind of trying to execute models like in good faith. So I'm not really familiar, but I'm sure there's people like looking at it because that definitely seems like a good idea to try to cache, you know, middle parts because they should still produce the similar results, but they're not going to produce the same results, and that's not something we do. You mean this?
Now, go back a bit more. Somewhere you had LoRa mentioned.
Oh, LoRa? Yeah. Oh, yeah. Yes, that is not something I mentioned because I didn't want to continue this talk even longer, but I think it was here. Yes, LoRa is one of the things we support. Yes, so you can have multiple different LoRa adapters on the same model running at the same time. That is supported. Yes, of course. But you know, if you want a single server to support multiple LoRa adapters, then you can do it.
I heard, of course, the pitch for any hardware or any model and whatnot, but I have to ask. But I'm curious about where you see macOS hardware coming, or any active exploration for that.
Yeah, so I think, you know, macOS is really doesn't fit the kind of primary goal of vLLM, which is large hardware, like a lot of requests and users, right? Data center, like large batch size. I think that's a reason it's less prioritized, but it's definitely a goal to have it supported because, you know, VLM isn't just like something we want users to like deploy in some data center and forget about it. Like we want it to be easy to work with as well. And so obviously like making it run on Mac to prototype and work with quickly with small models and then go deploy later on some large machine is a goal. It's just, you know, the priority is like large data center hardware. Like right now we're really focused on getting like the Blackwell performance as best as possible. We're really focused on, and this is a good segue into some future talks, into like multi-node, like kind of like distributed serving deployments and so on. And so I think there's an ongoing effort for Mac, but I'm not sure exactly when it's going to happen. All right. Thank you.